I've already made the statement that momentum is always conserved. So let's consider the conservation of momentum. Firstly, Newton's third law is always obeyed. There are no known exceptions. No violations have ever been discovered, nor are anticipated to be discovered of Newton's third. F1 on 2 is always equal to minus F2 on 1. Object 1 on 2, opposite to object 2 on 1. Every particle that makes up the body, or the multiplicity of bodies interacting, every particle in contact with another experiencing a force has an equal and opposite reactive force applied to it. And anytime some force occurs, it occurs through time. So we can multiply both sides of this by delta t, since the interaction time is always the same. You can't interact in a way that's isolating a particle. So the time of interaction is the same, and the force is the same. Well, F delta t is J, impulse, so impulse on object 2 is minus the impulse on object number 1, which also says the change in momentum of object 2 is equal to the negative change in momentum of object 1. Well, how about the total change in momentum? We just want to say total momentum change. We'd have to specify all the objects. The change in the first one plus the second one plus third, fourth, fifth, sixth, whatever, all equals 0 if the change in one is the opposite change in the other. So there's no limit to the number of particles or objects interacting. But when you consider the entire amount of change, it's always 0. We can write this in a couple ways. First of all, we can say that the total after an interaction is the total before, where the prime symbol just means after. So momentum total prime equals momentum total. Or we can just say that the total change in the momentum equals 0. Those are the two ways to express the same thing. This is in an isolated system where the total change is 0. Total change could be written in a practical sense for two interacting bodies as delta P1 equals minus delta, I said P, I should say rho. Delta rho 1 equals minus rho 2. Two bodies interacting, one change would be the opposite of the other. Isolated system simply means that there are no outside forces, or if there are any outside forces, they cancel. Well, let's consider our ideas of momentum and kinetic energy and apply it to a skateboarder race across an interval of distance x. There they are. One is 2m and one is m. The same force will be applied to both of these dudes. All right, and we're going to decide who has the greatest kinetic energy and who has the greatest momentum. Should be fun. Well, who crosses the line first? Probably don't have to consider that too long before you realize that the little one will cross the line first. Now, who has the greatest speed? And before you answer that too quickly, recognize that, yes, the little guy crosses first, but therefore the acceleration is not applied to m for as long a period of time as it's applied to 2m. So 2m gets this force applied for longer, so it's accelerating longer, so the time during which the speed changes is longer. All right, so what do you think? Who has the greatest speed? Well, maybe you've realized that we could consider the kinetic equation where the v squared is equal to 2ad, or v is equal to square root of 2ad. The d is the same. The acceleration is greater for this one. So the square root of that quantity is still greater. So yes, indeed, m has the greater speed when they cross the line. Well, maybe a better question is, who has the most work performed on them? Which one gets more work done? You say, oh, let's see. Oh, work total is delta k, and the one has greater speed. This guy has greater speed that we just determined, but this one has greater mass, so it's not real obvious, is it? Well, let's get a little more fundamental. Delta k is work total. F x. So this force is applied across x. The work done is the same for both. Therefore, the same kinetic energy that both have when they cross the line. Well, now, what about the momentum of the two skateboarders? Who has the most momentum, or are they the same as well as the kinetic energy? Momentum being mv, F delta t. Now, the force is the same for both. That was part of the problem. So who takes the longest time to complete the race? In other words, which one has the greater delta t over this F? Well, of course, that's the 2m, isn't it? Thus, the 2m has greater momentum. Well, I wonder how much. While the kinetic energies are the same, and the speed is greater for the little guy and less time, the momentum is not the same for both. So let's consider how much difference there is here. So we have 1/2 mv squared, 1/2 of 2m v squared is equal to 1/2 of the 1m times its speed squared. Now, halves go away, the m's go away, and we can take the square root, and velocity of the 1m equals square root of 2 of the velocity of the 2m. Now we know quantitatively the relationship between the speeds at the end of the race. So the ratio of the momenta equals the mass times velocities, and so there they are. Now the m's go away again. Now we can express the velocities as such, but recognizing that velocity of the single mass is square root of 2 times the velocity of twice the mass. So we can replace it and then divide it out, and we have square root of 2. So the ratio of the momenta is rad 2 in this case. Let's work out the momentum in a two-dimensional collision problem.
Oh!
And this one involves Troy, 75 kilograms, and Jenny, 50 kilograms, is going to hit into him at 13 meters per second and bounce off 10 meters per second, 37 degrees from her initial direction. And then they move frictionlessly after the event, and hopefully that's commensurate with their relationship as well. And what is Troy's velocity after this collision? Well, the total momentum in the x direction is the total momentum in the x direction after the collision. So we have the fact that we're dealing with a vector quantity. Since it's two-dimensional, we have to consider both dimensions, x and y. So the total in the y is the same before and after as well. Now let's check out what Troy's velocity is after the collision in the x and y, and then of course we can combine them. So afterwards, we have the situation. We have little m, or Jenny's mass. She moves off at 37 degrees at 10 meters per second, and Troy is going to be discovered here. So some questionable angle and some velocity of Troy after. So the total momentum before is total momentum after. Let's first consider the x direction. We'll do the full total momentum in the x equation, which is mass times velocity of Jenny, mass times velocity of Troy, and that's equal the same quantities after. Mass of Jenny, velocity Jenny, and mass Troy, velocity of Troy after. So there it is. And now let's do the same. Let's bring that together and do the same thing in the y direction. Now by bringing it together, I mean let's find Troy's velocity after the collision, which is solving it. There it is. Let's plug the numbers in. 50 times, that's the mass, times the quantity. Jenny's x velocity, 13. It's all in the x, right? That's why this is 13. All of her velocity is in the x. Minus the velocity of Jenny in the x times the mass, which is after the fact, which is 10 cosine of 37, divided by Troy's mass of 75, and that's 3.34 meters per second, I. So now we know his x velocity. Now let's do y. Total in the y is total after and that's 0. Because all of it was contained in Jenny's initial motion, and she had no y momentum. So after the collision, there's got to be no y momentum. But she does have y momentum, thus Troy's momentum in the y direction is the opposite. So when we add these momenta together, we have to get 0. So the velocity of Troy in the y direction is simply the negative of Jenny's momentum in the y over Troy's mass. Plug the numbers in, out pops minus 4.01 meters per second. So that's the J quantity. Let's get the magnitude of his, so let's get his speed, square root of the sum of the squares. Gives us 5.22 meters per second. And the angle, inverse tangent of the y over x, there it is, minus 50.2 degrees, with respect to the direction that Jenny was originally moving. How about the change in kinetic energy during the collision? So we're considering the total kinetic energy before and after. So it's a combination of both of their kinetic energies. So we have that delta K is K2 minus K1. K2 is after, K1 is before. So after is Jenny's kinetic energy and Troy's kinetic energy after the interaction. And before is Jenny's and Troy's. Of course, Troy wasn't moving to begin with, so it's 0. So let's expand each term. 1/2 mv Jenny squared prime plus 1/2 m Troy v Troy prime squared. It's hard to get all that in. Minus 1/2 mv Jenny squared. And now let's plug numbers in. Half of Jenny's mass, 25 times 10 squared, plus 37.5 times 5.22 squared. We just solved for Troy's speed after. Minus 25 times 13 squared. And there you go. Minus 703 joules. So 703 joules were lost to heat in the interaction.